You were working on this last time, finding the derivative of these couple things here using one or the other of the definitions. A polynomial like this works fine with the first definition I gave you, the derivative of that. So you could say f prime of x if you're using that type of symbol, or you could say df dx if you're using the other kind of notation. Start with this part of it, right? F of x plus h minus f of x. Probably at the beginning it's good to write the definition first. That's the slope of the secant line. It only becomes the slope of the tangent when you push this to becoming 0. Okay, when you push the 2 points together. Right? Just this expression is the slope between 2 points that are actually apart. And then maybe look at the actual function here, x plus h cubed, except I probably want to still write this. Limit as h approaches 0 of x plus h cubed minus x cubed over h. After that, it's just using some algebra that you hopefully know from before. Maybe if you learned something in grade 12 about how to expand this, you could do it a little more efficiently, right? Because you learned that binomial theorem that you probably aren't going to use very much except for maybe right here to save yourself a bit of time. You know, all those hours you spent learning it in grade 12, it might save you 30 seconds now, so it was completely worth it. X plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed, right? And then minus that. This is equal to that whole thing, all right? And then we need the bottom part of it. You need the h. If this works out the way you expect it to, the first term here is going to cancel out with this, right? The first term is going to cancel out. No matter what power I started with here, this is going to be a key to a shortcut that you're going to learn later. So just notice that whatever power I have here, the first term is going to cancel out and when I simplify it here. So I could simplify that and make it, without the first term here, I can make it 3x squared h plus 3x h squared plus h cubed, right? Because we have that and that disappearing. And we need, of course, the bottom part here. At this point, then you can simplify that, get rid of the h. Limit as h approaches 0 of, that simplifies to 3x squared, right? Because each of these, one of the h's is going to cancel from each of those things. So I got 3x squared plus 3xh plus h squared. Now you get it to the point where you can put the h in. You can deal with the h being 0. So what does that give me here? I can actually evaluate this limit. 3x squared plus 3x times 0. Right? You're putting in 0 for h here. Plus 0 squared. What does that give me? It's not going to work. Yes, it is. Run out of room, you just make more. What does that leave me with here? It leaves me with 3x squared, right? Plus 0 plus 0. Or just 3x squared. Right? Just 3x squared. This is the derivative of this function. If f of x equals x cubed, f prime, okay, the derivative, if that function f is 3x squared, f prime is, sorry, I said it wrong. If you start with x cubed, you get 3x squared as the derivative. This gives you the slope of the tangent line anywhere on this function. Now I put this in here because I do want you to connect it with what does it mean graphically. If you graph it on calculator or on software, you can maybe make some more sense of it here. The black line in the center there is x cubed. It's that function, that curve, x cubed. You've seen it before. And this purple one is 3x squared. So the slope of the red line, that's the slope of the tangent. The value of this purple curve, the y value, is the slope of the red line at any point. So we got the equation of the red line up here. That's the equation of the tangent line. So as you move this across here, right, in the center, it's 0, right? The slope of that is 0 in the middle. As you start to move this across, the slope of the tangent's getting more and more. And if we stop right wherever I was there, which is probably easier just to do that, the slope of that red line is 3. The value of this function is 3, right? If you sub in the number into this function, it gives you 3, right? 3x squared when x is 1 is 3. So this number, the y value of this function matches the slope of this. This function gives you the slope of that. As you keep increasing it here, it's going to go higher and higher, right? This is 5.24, this is 5.24. If you go to the other side here, okay, it's positive, right? Because it's really steep positive, so this is high up. This is going down because the slope of this thing is going down. Okay, slope of the red line is going down. It goes down to 0 in the middle, so the purple curve drops down to 0, and then it starts going up again. We're going to work on throughout this unit drawing the graph of the derivative from the graph of the original function. But that's the connection anyways between the two of them. Now the other one here, just using the alternate definition. Alternate definition for this. The reason that the regular definition doesn't work is because if you write limit as h approaches 0 of f of x plus h minus f of x over h, this ends up being square root of x plus h minus square root of x over h. And there's not really a way to simplify that algebraically. There's nothing you can do to simplify it and then be able to divide the h's. So instead, you can try using that alternate definition. With square root functions, it works quite well with that alternate definition. The alternate definition is just setting it up f of x minus f of a over x minus a, right? And then it's as x approaches a. So you have some kind of a curve here. You have x, you have a, you have f of x, and you have f of a. This one's actually simpler to understand what it is. It's the slope between 2 points, y values difference over x values difference. So if you have square root of x minus square root of a, I think I gave you a hint last time on how you can simplify this. You may or may not have been successful with that. You can actually do it two ways. You can factor this as a difference of squares. I'm going to write it over here. You can write the bottom as, like you could write this expression as square root of x minus square root of a over, you can factor the bottom as square root of x minus square root of a times square root of x plus square root of a. These two factors multiply to give you this. So you could factor it like that. Or you could say, if I want to try and deal with this here, what I could do is multiply by this on the top and the bottom. Okay, or sorry, multiply by the conjugate of that. If you multiply by the conjugate of that like you did with trig identities, you can simplify it. If you factor it like this, you can cross off those two factors. If you multiply by the conjugate, root x plus root a over root x plus root a, and then write what it's equal to here, the top two things multiply to x minus a. Right? These two things on top multiply out to x minus a. And you got an x minus a on the bottom, but then you also have a root x plus root a. So either way you're doing it, whether you're factoring it and canceling, or if you're multiplying by something over itself, you're going to end up with the same thing because I can cross these two off now. And what am I left with here? Either way you do it, you're left with 1 over square root of x plus square root of a. And at that point, then you can evaluate the limit because it's not 0 anymore. The reason you couldn't do it up here is if you let x approach a, meaning if you sub it in, right? If you put a in for x, right? Just like we did up here when we were doing as h approaches 0, at some point we put 0 in for h. At some point we put a in for x here. You can't put a in for x here because you get 0 on the bottom. But at this point you can because it's not going to give you 0 on the bottom. So if I make more space for myself here. Okay, if you make this now 1 over root a plus root a, you get 1 over 2 root a. 1 over 2 root a, or in other words, 1 over 2 root x, right? For this function here, square root of x, its derivative is 1 over 2 root x. That's kind of a way to use that alternate definition like that. Maybe don't get hung up in all the steps here. First and foremost, I want you to know what the derivative is. If you graph this and you graph this function down here gives you the slopes of this curve anywhere, right? If you want to know the slope of the square root of x curve, just look at this one. We can go back to this thing and change it if this is going to work. Maybe we'll pause this while I change this. As you move this along, the slope of this curve, right? The slope of the square root curve, which you can see by this, right? This function here, this equation is over here. The slope of that curve is the y value of this point. Okay? If you see what this point is here. Okay, the y value of this purple curve here is the derivative. Right? Because this function is the derivative, it's the slope of that line. Slope of the tangent of this is that function. That was totally not worth spending all that time creating this. Well, I mean, other than just thinking the line is really steep here, so that line gets that purple curve has really high y values. As you start going across, the slope of the square root function gets less and less. So this is going lower and lower. If you kept going to the right, the slope of this just keeps going lower and lower, but it's never going to be 0. It's always going to be going up a little bit, so this just trails off. Okay? So that's the connection to make right now, is just think about the graphs, right? Are we okay with this, possibly? I made some practice here that hopefully is really easy to do, because all you have to do is say what the original function is. If this is the definition of the derivative, what is the original function? That's all I'm asking you here. What's f of x? So instead of having you write out the definition a million times, I wanted it to be quick so you can look at the expression and see what the original function was. And then the last one here, or the second part here, I want you to write out a definition for the derivative. So if this is the original function, write out a definition. You don't have to actually evaluate it, because some of them you won't be able to simplify it, but write out a definition using limits, right? Limit as blah, blah, blah. Take a few minutes to do that, and then we'll look at the other couple parts of this.